We're going to do some analysis on how the Kalman filter behaves. And we'll start with one-dimensional analysis because it's going to be the most simple. Suppose we want to estimate an unknown constant. So, what kind of model will we use? Let's assume that xn is equal to xn minus 1. It's a constant, it doesn't change. And we have observations. The observations will be noisy. So for this particular model, we would have a equals 1, and we'll have c equals 1. For the noise, our process noise is 0. Things don't change. And the observation noise is just going to be a single random variable with a variance of sigma v squared. So let's explore a couple situations. We know how we would handle this, I think, under normal circumstances, as in not the Kalman filter framework. If we had a single measurement, y1, what is our best guess? Well, with no other information, it would just be x hat of 1 is equal to y1. Okay. What if we had n measurements, y1 through yn? In that case, we would probably do something like the average 1 over n times the sum over I from 1 to n of yi. Well, the Kalman filter gives us a little bit more that we can do. First, maybe we have reason to believe that x is, for example, 100. How would we then build up an estimator for x hat? Well, there's not a particular right answer. Not yet, anyway. But perhaps we could just say that x1 would be 100 times some constant beta plus our observation y1 times 1 minus beta. So if we choose for beta close to 1, we are basically trusting our initial belief more than we trust the observation. And with beta close to 0, we're trusting the observation more than our initial belief. So over time, as long as beta does not equal 1, this will eventually turn into the exponentially averaged observations, and kind of approximate what we had right above, except that once again it's exponentially averaged instead of just a straight up average. Okay, so those are different ways we could approach this. Let's now look at the Kalman filter framework and see how that would work for us. We need to choose our x hat of 0. For example, the 100 that we chose up above, and we need to choose our P0 given 0, which is our uncertainty. If we are certain that x hat 0 is correct, then our uncertainty is 0, and we choose P of 0 given 0 to be equal to 0. Alternatively, if we have no idea about our initial guess, then we would choose a large P. It may be that we just don't have any idea about anything. So in this particular case, we're going to start out by choosing P0 given 0 to be 1 for now, and we'll talk more about our choices later. So for reference, I've put the Kalman filter equations over here on the right. And let's see how things change when we go with our current situation. Let's see. A is equal to 1, so we would have x hat n given n minus 1 is equal to x hat n minus 1 given n minus 1. That's our prediction step. We predict that it doesn't change. For P, since A is equal to 1 and QW is equal to 0, it's just going to be the same as well. Okay, the Kalman gain, that's an important one. Since P n given n minus 1 and is equal to n minus 1 given n minus 1, I think we might just simplify things and get rid of the given. I'll change that in just a moment. For now, we have C is equal to 1. So that would be P n given n minus 1 times C transpose, and inside here we have 1 times P n given n minus 1 times 1 plus sigma v squared. This is a scalar quantity, so we can actually write it like this: P n given n minus 1 v squared. Okay, now we can give our observation-based state update. And this is K n times yn, our observation, minus our predicted value. And then finally, we have Pn given n is equal to 1 minus Kn times P n given n minus 1. Which, let's go ahead and just make this simpler here. It's equal to n minus 1 given n minus 1. Okay, since we have this actually in both cases here, where this and this are the same, let's go ahead and say that P n is P n given n, and P n minus 1 is P n minus 1 given n minus 1. That'll just simplify our notation just a bit. So using that new notation, let's go ahead and finish simplifying for Pn. Pn is equal to, actually I'm going to give some space here, is equal to 1 minus k, but k is equal to p n minus 1 over p n minus 1 plus sigma v squared. And that's all times p n minus 1. We can simplify that by multiplying up top and bottom by p n minus 1 plus sigma v squared times that 1. We end up getting then p n minus 1 sigma v squared over p n minus 1 plus sigma v squared. Okay, we can solve for this recursively, assuming that we have p0 is our initial guess. Then p1 is going to be p0 times sigma v squared over p0 plus sigma v squared. In this particular case, up above, remember I said let's just assume that p0 is equal to 1. So we'll do that, and this gets us sigma v squared over 1 plus sigma v squared. Following along, we can do 2. That would be p1 sigma v squared Wow, we have a lot of sigmas in there. Okay, we can divide out sigma v squared from the top and the bottom and multiply by uh, 1 plus sigma v squared on the top and the bottom, and that gives us this quantity, with those disappearing, giving us sigma v squared over 2 plus sigma v squared. So at this point we can use induction and find out without too much effort, and following the same procedure, that we get sigma v squared over n plus sigma v squared. In general, and I didn't do it the general case here because it's just a lot more writing, but it's not necessarily more difficult. So there we are. Next, if we come back and we look at our K, our Kalman filter gain, we can simplify this a little bit. as we've already discussed. We get something like that, and k now is going to be equal to p0 over n p0 plus sigma v squared. Finally, we can do our state update, our estimate update. And we're going to do the same trick we did before, which is that since x of n given n minus 1 is the same as x of n minus 1 given n minus 1, let's go ahead and change this by let xn equal x hat n given n, and x n minus 1 would be x hat n given n minus 1, which is just equal to x hat of n minus 1 given n minus 1. So given that simplification, we can now write the equation like this. So putting that all together, we have x hat of n, x hat n minus 1 plus p0 over n p0 plus sigma v squared times the error term So, a few observations here. One, as n goes to infinity, this quantity right here goes to 0. In other words, we stop updating. And you note once again that this is regardless of any particular observations of x. This is not a function of x. Regardless of what x is doing, as n goes to infinity, we stop updating. So to simplify this discussion a little bit more, let's just define a new variable, bn equal to p0 and p0 plus sigma v squared. Now, if you're astute, you might have already noticed that this is identically equal to the Kalman gain. I'm just actually putting in this other form so we can relate it to what we did earlier and simplify things. So in this case, we have x of n is equal to x hat n minus 1 plus beta of n times y of n minus beta of n x hat n minus 1, which can now be rewritten as x hat is equal to beta n y of n plus 1 minus beta of n times x hat n minus 1. Now is a good time to go back and look and see that indeed is very similar to what we had here. So here, where we have the 100, we would now have our x. And also notice that this is backwards. In this particular case, we have beta times x and 1 minus beta times y, whereas back here, it's the other way around, beta times y and 1 minus beta times x. And so the sense is upside down. But it's exactly the same type of thing. It's a recursive equation, recursive smoothing on our x. However, beta is not constant. Look at that. So at the beginning, when n is equal to 1, if p is large, then we're essentially placing, if n is equal to 1 and p is large, then beta is close to 1, and we're placing a lot of emphasis on our previous x. However, as n becomes very large, beta becomes very small. As beta becomes very small, we're placing more emphasis on our previous estimate. So in that sense, this is a recursive average, but it's a recursive average that takes into account how much averaging we've done so far and how certain we are about our particular observations. And so this recursive average changes in its characteristic over time. Finally, as n becomes large, ignore observations and just go with our previous guess. Well, there is, of course, a problem with ignoring observations. What happens if our model is wrong? We assumed that x didn't change, but what happens if it does, ever so slightly, or eventually it starts changing ever so slightly? We're talking about the underlying system, the true x. In that point, we would diverge. So what can we do? We can still use the model if we think it's reasonably close, and we add in some noise to account for the fact that maybe our model is wrong. That way, if x changes, then we've taken into account the fact that it can change, and it will keep our Kalman gain from ever going completely to 0. Note, we can have two possible problems. One is that xn is actually equal to xn minus 1 plus some zero mean noise. In this case, the expected value of xn is equal to x0, but the variance will increase. This is what we call apparent divergence. And we will have great confidence as to what our actual value is. We'll eventually freeze but the true value will be wandering around someplace else. The other type is we can have actual divergence. If we have something like xn is equal to x n minus 1 plus some constant plus noise, for example. In this case, we will have actual divergence. We will get more and more confident about how things are looking, and our p will go to 0, but we will be in another part of the universe from where we actually should be. In either case, we can avoid catastrophic failure by having a non-zero W in the model. So here is the great truth. Wn can compensate for a poor model. Of course, having a good model means that our tracking will be better, but having a Wn that is larger can keep our system at least behaving reasonably, even if our model is bad. So we'll explore a little bit more complicated situation, as in not just one-dimensional, in the next lecture.